The TimberPro TL755D feller buncher equipped with the Quadco 24B saw head is a high-performance forestry machine designed for efficient tree harvesting. Operating in Oregon's dense timber stands, the machine combines hydraulic precision with robust cutting capability. The 24-inch circular saw, powered by TimberPro's advanced hydraulic system, allows the operator to fell trees quickly while minimizing wood damage. The feller buncher's articulated boom positions the saw accurately for cutting at base height, while the integrated bunting arms securely hold and gather multiple stems before processing. The hydraulic control system ensures smooth saw rotation and boom movement, reducing operator fatigue and improving safety. With advanced sensors and maintenance-friendly design, the TL755D optimizes productivity, delivering precise, clean cuts in diverse terrain conditions. This combination of TimberPro TL755D and Quadco 24B provides a reliable, high-capacity solution for professional forestry operations. The uphill cable logging system with the MM Sherpa Universal integrates both retrieval and forced payout functions through a single auxiliary cable. This dual-use cable enables precise positioning of the carriage while simultaneously handling a loader crane or processing device. The carriage is drawn along the track via the retrieval cable, which runs over two UML rollers positioned at the downhill end. This arrangement ensures controlled and immediate response during both carriage positioning and mainline payout. Side-mounted guide rollers maintain cable alignment and prevent interference with timber movement. The retrieval cable is wound onto a drum within the carriage, and during payout, it drives a friction mechanism that actively releases the hauling line. During load retrieval, the cable rewinds automatically for the next cycle. A hydraulic pump, powered by carriage movement along the track, supplies pressure to operate the clamps. At the landing zone, the carriage halts automatically, enabling precise control over the work lines and facilitating secure placement of logs. Forced payout significantly reduces operator effort and improves efficiency, particularly on flatter terrain. Trees are bundled using joker slings to maintain stability during transport. The system supports a 3-cable gravitational mode, where the auxiliary cable assists the hauling line during load transport. Switching between standard and 3-cable operation is simple. The cable is rerouted through dedicated rollers, and the control system automatically adjusts cable movements, eliminating additional operator input. The Wanderfalco with mm Sherpa is engineered for medium transport distances, ranging from 400 to 650 meters, optimized for professional uphill extraction of medium to heavy timber. Its carriage, cable drum system, friction mechanism, and hydraulic clamp integration ensure precise, repeatable, and safe operation. Forced payout, dual-function cables, and automated control enhance productivity while reducing manual intervention, making the system a highly efficient solution for modern forestry operations. Plywood begins as whole logs, which are transformed into thin sheets of veneer through precise milling. At Pacific Veneer in Aberdeen, Washington, logs are selected carefully in the forest to meet strict specifications. Upon arrival at the mill, logs are loaded onto the debarker deck, where bark is removed before they are cut into 10 3/4 inch sections on cutoff saws. These log blocks are then loaded onto bunk belts by operators and transferred into a heating vault for approximately 16 hours. This conditioning softens the wood fibers, preparing them for peeling. Each block is scanned and positioned in the lathe in-feed by a charger, ensuring optimal XY centering to maximize yield. The lathe rotates the block, while a peeling blade removes continuous sheets of veneer, which then exit onto a conveyor for further processing. Peeler cores are repurposed for pallet stock or landscaping timbers. The veneer ribbon passes through a rotary clipper, which removes defects along the leading edges. Sheets are then separated according to moisture content to ensure uniform drying. Dryers operate continuously 6.5 days per week, reducing moisture content to 8% or less. Following drying, sheets pass through a Ventec grader, which assigns quality grades based on surface and structural criteria. Finished veneer sheets are banded with a strapper and stored in a dry environment to maintain stability until shipment. These sheets are then supplied to plywood mills, where they are used for sheathing, underlayment, and other construction applications. Throughout the process, sustainable forestry partnerships are essential. Close collaboration with suppliers ensures a consistent log supply while supporting responsible forest management. Pacific Veneer's integration of precise scanning, controlled drying, and defect removal guarantees high-quality veneer production, maximizing yield and minimizing waste, while maintaining the structural and visual standards required for plywood manufacturing. Green Defender plywood is engineered for fire retardancy, strength, and durability. Fabrication begins by selecting high-quality logs, carefully selected quality logs cut to required sizes. Bark is removed using a debarking machine, producing uniformly thick and smooth blocks. These blocks are then peeled into veneers using a spindleless peeling machine. The veneers are softened in a tenderizer to relieve internal stresses and increase flexibility. Next, veneers are treated by immersion in a hot water bath containing fire-retardant chemicals. Controlled drying follows in a mechanical dryer, ensuring uniform moisture reduction to 6 to 8%. Veneers are then composed into standard 8 by 4 foot sheets using a core composer machine, avoiding gaps and overlaps. The assembled core veneers pass through an 8-foot glue spreader with specialized fire-retardant adhesive. Face veneers are added, and the layers are pre-pressed under fixed pressure before hot pressing, curing the plywood under controlled temperature and pressure. Finally, boards are dipped in fire-retardant nanochemical solutions, rendering them fire, borer, and termite resistant. Each sheet undergoes laboratory testing for fire penetration, flame duration, and burning rate. Only after passing these tests is the plywood packaged and prepared for delivery, ensuring Green Defender plywood meets marine grade, fire retardant, and durability standards. Production starts with raw logs mounted onto the log feeding system and secured in position by servo-controlled rollers. These logs are then fed into a spindleless rotary peeling machine, a core component in modern plywood lines. Without a central spindle, the log rotates using friction rollers, while a servo-driven knife carriage precisely advances, peeling off continuous sheets of veneer. These machines typically support log diameters from 40 millimeters up to around 600 millimeters, depending on the model. Veneer thickness can be accurately controlled from approximately 0.4 millimeters up to 4 millimeters. Speed is adjustable. Some high-speed units operate from 30 to 120 meters per minute, thanks to an inverter-driven system and servo motors. Double roller drive designs maintain log stability and ensure consistent peeling pressure. while high-precision lead screws guarantee accurate feed and veneer thickness. Finished veneers are continuous and uniform, making these machines ideal for high-volume plywood production and efficient use of raw material. Spindleless peeling thus offers high productivity, lower maintenance, and consistent veneer quality. The LVL production process begins with the storage of small dimension veneers, typically 1270 x 630 millimeters, in a controlled environment to maintain consistent moisture content. These veneers are then transferred to high-capacity drying systems, where hot air or conveyor dryers reduce moisture to the target level, ensuring optimal adhesion during lamination. Next, veneers are composed into cross and length layers. Cross-veneer composing ensures structural stability and strength, while length veneer composing creates continuous boards suitable for the final LVL dimensions. An intelligent transfer system moves the veneers efficiently between storage, preparation, and production stations, minimizing handling damage. The system integrates with a production planning center and an intelligent out-of-warehouse system, which automates the selection and feeding of veneers based on product specifications. The robotic layup line precisely arranges veneers for pressing, accommodating veneers as thin as 0.5 millimeters for surface layers, or thicker core layers, such as 20 millimeters OSB. MDI adhesive is applied using spray systems with precise control, consuming less than 40 grams per square meter, ensuring strong bonds while minimizing waste. The top surface veneer undergoes microwave preheating to improve resin penetration and adhesion. Boards then enter the continuous pressing system, which applies uniform pressure and heat to cure the adhesive. Advanced sensors maintain thickness deviation below 0.20 millimeters, even for LVL boards up to 90 millimeters thick, or lengths up to 20 meters. After pressing, raw board handling systems allow further processing or surface finishing. LVL can be laminated with 1 millimeter MDF or 0.5 millimeters thin veneer surfaces, offering versatile applications. Quality tests, including a 72-hour boiling water test, ensure boards are crack-free and durable. The entire production line is coordinated by an intelligent production center, integrating storage, drying, layup, pressing, and finishing, delivering high-strength, precise, and high-quality laminated veneer lumber suitable for structural and architectural applications. The G5000 TLE telescopic loader delivers a 4.35 meters lifting height with precise hydraulic control. Its articulated pendulum joint ensures stability and traction on uneven terrain. The ergonomic cabin, adjustable steering, and joystick-operated functions optimize operator comfort and efficiency, making it ideal for high-reach lifting, loading, and material handling in demanding environments. The production of a Raute particle board and Prism TFL panels begins with 100% recycled or recovered wood chips and shavings. Trucks unload the material into designated collection areas, from where it is conveyed into storage silos. Milling separates surface and core material, while a series of shakers refine and filter the wood to remove contaminants and ensure uniform particle size. Core and face materials are processed separately to provide consistent quality for lamination and downstream operations. Next, the wood enters large drying units. Moisture content is reduced from 40 to 50% in chips and 15 to 20% in shavings to 2 to 3% for core material and 6 to 7% for surface layers. The dried material is then blended with resins and additives. Specialized formulations allow production of moisture-resistant, fire-rated, and ultra-low emission boards. Blended layers are fed into a continuous press, where heat and pressure compact the wood into boards. This stage ensures precise control over thickness, density, and particle geometry. Pressed boards are cooled on rotating racks and periodically tested in the Quality Assurance Lab for strength, density, and compliance with standards. Sanded and cut to required dimensions, selected boards proceed to the thermally fused laminate line. Decorative overlays, including wood grains, solid colors, and abstract designs, are saturated with melamine and resin, then thermally bonded under high temperature and pressure. This process creates durable UV and chemical-resistant surfaces. Finally, finished boards are stacked, packaged, and stored in the warehouse, ready for distribution. Araco particle board and Prism TFL panels are used in cabinetry, furniture, fixtures, and laminated surfaces. Throughout the production cycle, environmental, safety, and quality standards are rigorously maintained to deliver reliable, high-performance products. Every piece of particle board begins its journey as ordinary wood chips. But through precision engineering and advanced machinery, these small fragments transform into high-strength, versatile panels used in furniture, cabinetry, and construction. The production of particle boards begins with wood chipping. Logs and wood residues are processed in a wood chipper, reducing them into small, uniform chips suitable for board manufacturing. The chips are then transferred to large industrial dryers, which reduce moisture content to the required level for processing, ensuring optimal bonding during later stages. Once dried, the chips are screened and separated into two distinct sizes: fine particles for surface layers and coarser particles for the core. This separation is critical for achieving uniform density and strength in the finished board. The next stage is gluing, where high-quality adhesive is uniformly applied to the chips. The resin-coated material is then conveyed to the forming line. Here, mats are formed according to the specified board thickness and density, ensuring even distribution of material and resin across the surface and core. Following formation, mats undergo pre-pressing, which compacts the material slightly and cuts the mat to the required board length. This step improves handling and ensures precise dimensions before final pressing. The hot press stage is next, where the mats are pressed under high temperature and controlled pressure. This stage consolidates the layers, activates the resin, and provides the board with mechanical strength and stability. After hot pressing, the boards proceed to edge trimming, where excess material is removed and panels are cut to precise dimensions. Sanding and calibration follow, creating smooth and even surfaces suitable for lamination or direct use. Boards are then optionally coated with decorative overlays in an impregnating line. Printed paper or decorative sheets saturated with melamine resin are applied, and a pre-press or final press bonds the decorative layer to the board. This process enhances durability, chemical resistance, and aesthetic appeal. The final particle boards are carefully inspected, packaged, and prepared for shipment. Throughout production, quality control checks are performed at each stage, ensuring consistent density, thickness, surface smoothness, and adhesive curing. These particle boards are widely used in furniture, cabinetry, flooring, and interior construction. By combining wood resource optimization, precise adhesive application, and advanced pressing technology, the process produces strong, durable, and environmentally responsible boards, establishing a long-term, reliable relationship with customers and the woodworking industry. The Raute Smart Plywood manufacturing process represents a fully integrated and highly automated solution for producing premium hardwood birch plywood. Designed to optimize both quality and material efficiency, the process covers every step from veneer peeling to the final overlay. The production begins at the Raute Smart Peeling line, where logs are processed with precision to maximize face veneer recovery. Utilizing SmartScan HD technology, the system continuously analyzes each log to determine optimal cutting paths. Auto-calibration ensures ongoing accuracy, allowing consistent veneer thickness and quality. Accurate clipping further improves raw material utilization, reducing waste while maintaining the structural integrity of each sheet. Safety systems are integrated throughout the peeling line, protecting operators and ensuring smooth operation. Once peeled, the veneers are transferred to the Meccano G5 drying solution. Here, temperature and humidity are carefully controlled to achieve the desired moisture content, preventing warping or defects in the finished plywood. The dried veneers are then routed to the face veneer composing line, where high-quality sheets are arranged and prepared for layering. Core veneer composing lines follow, designed to maximize the use of raw materials while maintaining precise alignment and consistency for the plywood's internal structure. Next, the trim saw line accurately cuts veneers and core layers to the required dimensions, ensuring uniformity and improving panel value. Scarfing and patching operations address minor defects, producing a flawless substrate ready for layup. The automatic layup system assembles the layers with precision, and high-performance hot presses apply controlled pressure and temperature, bonding the veneers into strong, durable panels. Finally, the overlay process enhances surface quality and adds functional properties such as wear resistance or aesthetic finishes. By overlaying premium materials, the panels achieve added value and are suitable for demanding applications in furniture, cabinetry, and construction. Throughout the Raute Smart Plywood production process, advanced automation, intelligent process controls, and integrated quality monitoring work together to maximize efficiency, reduce waste, and deliver consistently high-quality plywood. This comprehensive approach ensures that every panel meets stringent standards for strength, appearance, and performance, making Raute technology a benchmark for modern hardwood plywood manufacturing. The high-speed MDF engraving machine, often configured as a 1325 CNC router, is purpose-built for precision decoration and furniture work. It features a large working area of approximately 1,300 millimeters times 2,500 millimeters, enabling wide-format MDF panels commonly used in interior design. At the heart of the machine is a high-power spindle, typically 3.0 kW or up to 3.5 kW, capable of reaching rotational speeds from 6,000 to 24,000 revolutions per minute, depending on the model. This high RPM allows for fine detail engraving and fast feed rates without burning or tearing the MDF surface. The frame is constructed from welded steel square tubes to ensure rigidity and stability. Movement along the X and Y axes is managed by a rack and pinion drive system with linear guides, ensuring both high precision and durability. The Z-axis is typically driven by a ball screw, providing accurate vertical positioning. Control is handled by a DSP-based CNC controller, often with an optional USB interface for offline operation, making it possible to run jobs without constant PC connection. The machine supports standard G-code instructions and works with common CAD/CAM software used for furniture design and decorative carving. To handle dust created by high-speed MDF carving, the machine integrates a dust collection interface, ensuring safe and clean operation. The working table can be configured as a vacuum surface or T-slot, depending on whether parts need to be held flat or clamped more rigidly. In operation, the router rapidly traces detailed engraving designs, raised moldings, or inlays for furniture panels. The high-speed spindle allows shallow, smooth cuts, ideal for both decorative carving and functional grooves like joinery or panel profiles. After engraving, the machine can switch to trimming operations, cutting the panel to precise dimensions. Once machining is complete, the panels typically undergo sanding or finishing. The precisely carved MDF pieces are ready for lamination, painting, or direct use in interior decor elements like wall panels, cabinet doors, and furniture components.